and A cross B. Now this is the box product containing the vectors B cross C, C cross A and A cross B. Now this is equal to A, B, C, the box product of A, B, C whole square. Now why does this happen? Let's try to find it out. This is nothing but equal to B cross C dot C cross A cross A cross B. Now what we do is write this as equal to M. So this would be M cross A cross B. Now this is the vector triple product and this value would be equal to M dot B times A minus M dot A times the vector B into B cross C. Now when we write the value of M as C cross A, then we get the value of this as equal to A B C times A, and here it is B cross C. Now this would be equal to A B C whole square. Thus the value of the box product of B cross C, C cross A and A cross B is the square of the box product A B C. Thus this is A B C whole square. Therefore this and this gets cancelled and what we get is final value A dash B dash C dash is equal to 1 by A B C. Thus the product of these two is equal to 1. The second property is if A, B, C are non-coplanar, then A dash, B dash and C dash are also non-coplanar. And the third property is vector A into B dash is equal to vector A into C dash, which is equal to vector B into A dash, which is equal to vector B into C dash, which is equal to vector C into A dash, and which is equal to vector C into B dash, and which is equal to 0. The next is solving vector equations. Now we have solved so many equations in algebra, like a linear equation, cubic equation, quadratic equations and so on, to find the value of the unknown. Similarly, we solve a vector equation by finding the unknown vector from the given equations. So we'll be given a set of equations and from that we try to find out the value of the unknown vector. But how we do that? Let's try to understand it through an example. So the problem says that solve R cross A equal to B and R dot A equal to C. So we have been given two equations, R cross A equal to B and R dot A equal to C, and here R is the unknown vector and whose value we need to find. So let's try to understand how to solve such vector equations. So the given equations to us are R cross A equal to B, and let us say that this is equation number 1, and the second equation given to us is R dot A equal to C. Let us say that this is equation number 2. What we do is we take the first equation and cross multiply it with vector A. So R cross A would be equal to B cross A. Now this is the expression for vector triple product, and thus we know that this is equal to vector R dot vector A times vector A minus A dot A times vector R equal to B cross A. Also given to us as vector R dot vector A is equal to C. So we substitute this value over here to get C times vector A minus A square times vector R. The value of this is A square. So this would be equal to B cross A, or we get vector R equal to C times vector A minus B cross A whole divided by A square. Thus the value of R, which is the unknown, is equal to C times A minus B cross A divided by A square. So this is the way we actually solve a vector equation. Now finally, let's try to see some of the applications of vectors. So some of these applications make the study of vectors so important. The first application is finding the components of a vector B along and perpendicular to a vector A. So if we have been given a vector A and another vector B, then the components of a vector B along and perpendicular to a vector A. Consider this figure. This is vector A and OB represents vector B. Now the vector OA would be equal to the length of vector OA times a unit vector along the direction of A. So vector OA is equal to OA times the unit vector A. Now OA is nothing but OB cos theta. So if we consider this triangle, the length of OB cos theta would be equal to OA, and hence OA would be equal to OB cos theta into vector A. Now OB is nothing but the magnitude of this vector B. So the vector OA would be equal to modulus of vector B into cos theta times a unit vector along A. So this is the expression for the vector OA. Now we also know that cos theta is equal to A dot B divided by the modulus of vector A into modulus of vector B. So what we do is we put this value over here to get OA equal to modulus of vector B into vector A dot vector B divided by modulus of vector A into modulus of vector B times a unit vector A. So this and this gets cancelled, and what we get is A dot B divided by modulus of vector A times a unit vector. Now a unit vector is equal to vector A divided by modulus of vector A. So this would be equal to A dot B times vector A divided by modulus of vector A whole square. Thus the component of vector B along OA is given by vector OA, and this is equal to A dot B times vector A divided by the square of modulus of vector A. Similarly, we see that vector perpendicular to A is AB. Also, if we consider this triangle, then we see that vector B is equal to OA plus AB vector. So AB would be equal to vector B minus vector OA. We have just found the value of OA, which is this expression, and so AB would be equal to B minus A dot B times vector A divided by modulus of vector A whole square. So this is the way we find out a vector along and perpendicular to the direction of A. The second most important application of vectors is calculating the work done by a force. Now in physics we have studied that whenever a force is applied on a body, and if the body moves, then a work is done on the body because of the application of force. Now the work done by such a force is equal to the component of force along the displacement into the distance moved. So let us say that this is a body on which force is being applied. Now this is the direction of force. Let us say that this force makes an angle of theta with OM. Now this is the direction in which the body is moving. Let us say that this is represented by vector D. Then the component of this force along the displacement is equal to modulus of F times cos theta. So the magnitude of the component of force which is applied along the displacement of the particle is modulus of F cos theta, and when it is multiplied by the distance the particle moves, this is known as work done. So work done would be modulus of F times cos theta into modulus of T. Now this is nothing but the dot product of F and D. Thus simply F dot D represents the work done by any force on a particle. Thus the dot product helps us to find out the magnitude of work done on any particle by a force. Now again, this is an important application in physics. Now the moment of force gives us an idea of the tendency of a particle to rotate about any point or about any line on the application of a force. Now first let's try to understand the moment of force about a point. So let's try to understand how to calculate the moment of force about a point. So a force F is being applied, and this is the vector F. So this vector F represents the force. It is being applied at this point, and we have to calculate the moment of this force about the point O. Let us say that OA is equal to vector R. So the moment of force about this point is given by R cross F, and this is perpendicular to the plane of R and F. Thus the moment of force F about any point is given by R cross F. So R is the vector joining the points O and A. O is the point about which the moment is to be calculated, and A is the point at which the force is being applied, and the vector F represents force. The second is about a line. So the moment about a line is given by r cross f dot a cap. So this becomes a scalar quantity, as this represents a scalar triple product. Now a cap is a unit vector in the direction of the line. First we calculate the moment about any point which is given by r cross f, and when we take the dot product of this quantity with a cap is a unit vector along the direction of line, then it gives us the moment of the force about a line. Now last but not the least, let's study a very important property of tetrahedron. We can clearly see that this is a tetrahedron. It has got 4 vertices and 4 triangular faces. Now let us say that A, B, C, D represents a tetrahedron with A as the vertex. Clearly we can see that it has got 4 faces: ABC, ABD, ADC and DBC, and the 4 vertices. Now the volume of such a tetrahedron is given by V equal to 1 by 6 into the box product of AB, AC, AD. Here A is the vertex of this tetrahedron. So AB would be this vector, AC would be this vector, and AD would be this vector. Volume of a tetrahedron with vertices as A, B, C, D is given by V equal to 1 by 6 into box product of AB, AC, AD. Let's try to solve an example. Find the volume of a tetrahedron whose vertices are given by the coordinates 1, 1, 1, 1, 1, -1, -1, -1, -1, -1, and -1, 1, -1. So in this problem we have to find the volume of a tetrahedron whose vertices have been given. Let us say that A is represented by the point 1, 1, 1, B is represented by 1, -1, -1, C is represented by the point -1, -1, 1, and D is represented by the point -1, 1, and -1. So AB vector would be equal to -2j cap minus 2k cap. Similarly AC vector would be equal to minus of 2 times I cap minus 2 times j cap, and AD vector would be equal to minus of 2 times I cap minus 2 times k cap. Now we have just seen the formula for the volume of tetrahedron. So this is equal to 1 by 6 into box product of AB, AC and AD. So we have to find the box product of these 3 vectors. Now we know that the box product of these 3 vectors is given by 1 by 6 into the determinant, the elements of which are 0, -2, -2, -2, -2, 0, -2, 0, -2. This is equal to -4 by 3 into -2, which is equal to 8 by 3. Thus we get the volume of tetrahedron ABCD as equal to 8 by 3 units.